Hey everybody, and welcome back to Calc 3 Online. So this video actually marks our last video with new content for the year. Everything else after this will be review videos, which is kind of cool. And I think you'll find that this one's actually not too bad. This is actually a really powerful tool, and I can't really explain it when I first introduced triple integrals, but honestly, this to me is why triple integrals are so important. And it takes a long time to get here, but from the point that we learn triple integrals. But this is, to me, like far and above the number one reason why you really want to understand how to solve triple integrals. So there is one more theorem in this last chapter that's really big and really important, and this is what it says. It says that if you let E be a simple solid region, and I'll talk about that in a second, and S be the boundary surface of E, given the positive outward orientation. So we saw that with one of our vector forms of greens. This is kind of the positive. We also saw it with other theorems too, but I'm going to actually make a direct connection back to this. So this outward orientation is always the positive one for these kind of problems. And F is a vector field whose component function has continuous partial derivatives on an open region that contains E. Then it says that this surface integral, okay, so around the boundary surface of the thing, is actually just equal to the triple integral of the divergence of the field, okay? And if you remember divergence, right, it's just literally you just add up the partial derivative of x in the first component, right, plus partial derivative of y in the second, and blah, blah, blah. It's a very quick, easy computation. And so it's saying this surface integral, which can be really cumbersome and all that stuff, is actually just equal to a triple integral of a pretty nice computation in terms of vector operations. And this thing right here on the right is what we call total net flux. That's a formal term. And basically, the one thing you really need is this part right here. E needs to just be a simple solid region. And we've seen a lot of these. A sphere is a simple solid region. You can have an egg be a simple solid region. You could have a tetrahedron, which I am not going to be able to draw well. Let's do... Oh, I did it. A tetrahedron's a simple solid region. Basically, the regions that are, the definition of this thing is anything that is really type 1, 2, or 3. Back when we learned triple integrals, we talked about type 1, 2, 3 things. Those are what we call simple solid regions. They're basically closed and bounded surfaces. And so you can't have actually, there's going to be a problem we're going to do where the object is not a simple solid region, and we can trick it and make something that's simple and solid, and then you'll see. But a cube over here could be a simple solid region. So they're nice things. They're closed and bounded, type 1, type 2, type 3 things. And there is a really big connection here back to something we've already seen. So this down here, this is one of our vector forms of greens. And I proved how this one comes about. And we talked about it in one of our second curl and divergence video. And basically just talked about how there's this relationship between the line integral of the outward normal vector here and the divergence. Basically one way you can do a problem like this is you can compute the line integral of f dot n ds as you go around this thing, or you could do the double integral of the divergence of f. And it's basically just saying that at any given point, right, if you sum up the kind of changes of the vector field with the little normal vectors, right? And there's, obviously infinitely many, and the integral will sum all those different little normals up and the connection between those in the field, that connection is the same as just doing the double integral over this region R in here. the divergence. It's kind of like a measurement of how much stuff passes in and out of the planar surface. So what we're doing is we're just bumping that up. We're saying no longer am I concerned with just how much stuff passes in and out of a planar surface, but I'm basically concerned with how much stuff passes in or out of a, three-dimensional object, right? Like a sphere, an egg, a tetrahedron, a cube, stuff like that. This little picture I kind of wanted to talk about because I remember, I think I've said this a few times, but I started off as pre-med in college, and when I was pre-med, I remember doing problems where I would have to compute the total net flux of some sort of thing like water passing through a cell membrane, and you can compute like the total net flux and see that maybe more water is coming in or leaving the cell and all sorts of things like that. So you can kind of think of this as like a cell object, and this is maybe in a flow of water through it, and some comes in and some comes out, and you might want to know, is that total net flux positive or negative, that kind of thing. So it's basically just this picture, but scaled up a dimension. We're thinking of what is the overall net flow of things in or out of the simple solid region. That's the idea. Okay, and there is a proof in the book. You should read it. Stuart does an awesome job of doing a good proof of it, but it's going to take a little longer, and I don't really think we need to be able to do it. I just really want you to see how powerful this theorem can be, basically. So let's go through one of these. So I want to calculate the surface integral of this thing, where S is the cylinder, x squared plus y squared equals 1, and z is bounded by 0 and 2. So I'm going to start off, I'm just going to draw what that is, okay? So, we've got down here in the xy plane, that would be z equals 0, and then up, I'm going to say that's 2, up at 2 is the upper part of that cylinder, right? And if you think about it, to do this problem, there are 3 surface integrals. And so that's pretty time-consuming, right? There's a surface integral up here, right? There's a surface integral down here. And then you've got the whole, side of the cylinder all the way around, right, into the back and everything like that. So you've got 3 surface integrals you would have to do. We don't want to do that. We want to be lazy and do this way quicker. So this object is what we would call a simple solid region, right? It is just kind of one of these things or these things that I was talking about. So it should be fine to do divergence. And so that is definitely the way I would do this thing. So this problem, the way I would really do it is I would do a triple integral of the divergence of f dv over E, where E is just, defined by basically those 2 things. That's a very bad circle. E is defined by that kind of stuff. So if I get into this divergence part, the divergence is actually quite nice because the partial of this with respect to x, right, you're going to see there's a 3 pulled down, cancels there, you're just going to get x squared. And then the partial of this with respect to y, same kind of thing, you're going to get a y squared. And then partial of this with respect to z is just a 1. So the problem was set up to be really, really nice. And then if we're now back in a chapter 15 kind of setting, and we just solved this the way we solved a problem like this back in chapter 15. So I would personally switch to cylindrical coordinates. The problem is a cylinder, right, that we're integrating over. And so it's definitely a good setup for cylindrical. And this part would become r squared in cylindrical. And so if I do my switch to cylindrical, I'm going to have r squared for the x squared plus y squared plus 1 still. And then I have an r dz dr d theta as my Jacobian. And then I would go 1 to 2 in z, right, from the bottom of this thing to the top of this thing. And then 0 to 1 in the polar radial measurement, right, out. And then 0 to 2 pi for the full circle around, right? That's a really nice integral. I don't think I'm going to spend time doing it out. Nothing in there is really quite tricky. You get 3 pi, I'll just tell you. So it doesn't look like a lot of work, right? And that's kind of the power of it. If you think about, I really don't want to do it, but if you think about how much work it would be to do 3 surface integrals there, it's crazy. It would be a lot of work. You'd have to handle getting normal vectors and it's a lot. You got to parameterize things, and so you skip basically all the hard stuff, to be totally honest. Computing divergence of something is quite quick. I mean, this one was set up to be nice, but even if it wasn't super nice, it's still really fast. So one thing I just want to take a second to talk about is the divergence theorem on non-simple regions. So this region right here that you kind of think of as like, I look at it as like an avocado and there's the pit in there. So the region I want to do maybe divergence on is the kind of blue region, that, like the part that's between the outer blue shell and that red shell in there. And so it's kind of like the part of the avocado that you eat, if you want to think about it that way. I don't want the pit, is the idea. So that thing sort of has a hole in it, and so it's a non-simple region, right? And we did problems like this with greens too. Like you could have a thing where you have a hole, a planar kind of graph analogy to this thing, and we want basically everything in here. And the way we handled that, right, was we like cut it, and then we kind of picked, a direction around the upper part, and then we picked a direction around the lower part, right? And in here and here, they cancel out, and so you don't double add anything. And so if you take, in the end, you add this one to, let's do the red one up here. If you add the green and the red, right, you would still be able to apply greens to situations like that. And it just, there's like a negative that works in and things like that. So it's very similar for divergence, okay, divergence theorem. The idea is basically that there's going to be a negative normal that naturally comes into the problem. So we always consider the normal that sticks out as like the positive orientation. So if I wanted to set this thing up, okay, it would look like this. So the idea here is, if I'm talking about S1 being kind of the pit, the inner part there, N1 is that's the positive normal direction that I normally would want, right? But I want to be kind of pointing out of this, away from that, the opposite direction, because, if you think of the kind of shell region we're talking about here, the outer direction of the shell is always what we consider as the one we want. And so you basically just like split it into 2 surface integrals in a sense, and you just do, the negative of N1 in there, right, for the S1 being the kind of pit region. And then this one you could just take the N2. And so you can still do divergence in this situation. You just this divergence would basically just be equal to the sum of these 2 things, where there's like a negative that kind of comes out of. Oops, I dropped this should be, I wanted f dot n1, and then technically I guess that what I had could also be right, because I could just use that notation where there's bold s, but I don't do bolds too well in here, so let's just keep it this way. So just like greens, you can extend it to other non-simple regions. But I don't really plan to make you do a lot of those. It's just something I kind of want you to know that you can do. All right. This example is kind of interesting, though, because it's one where it doesn't seem like you should be able to use Green's divergence theorem, and then if you use a kind of a clever trick, it turns out you can, and then it actually becomes really nice. All right, so this is what's kind of interesting about this problem. So you've got S is the top half of the sphere, x squared plus y squared plus z squared equals 1. And so if you think of that region, okay, if like the top half of the sphere right there, it's not really one of those simple closed surfaces. But what we can do is we can kind of introduce a bottom disk in a sense, and then now you actually have one of these nice simple closed surfaces. So that's actually what we're going to do. And that bottom disk is, of course, just like x squared plus y squared less than or equal to 1. And I'm going to let that thing be called, I think, just like S1, okay? And what I'm going to do is I'm going to compute a surface integral across that surface, okay, which I can do pretty easily. And then what I can do is now I'm going to be able to set up an entire divergence theorem problem and do a subtraction in there where I take out that part, the surface integral across that, to get the surface integral across just the upper half of the sphere. So that's roughly what I'm about to do. For the surface integral across that disk, okay, it's going to be just like f dot ds. And notice that like the normal vector for this disk down here, right, would just be minus k, right? That would just be straight down. That's just like a nice consequence of this. So what I'm going to do for my surface integral is I'm just going to dot f with minus k. And then, what happens there is you basically just get the negative of this right in here. So you get S1 negative x squared z plus y squared ds. But z, this is all at the plane z equals 0, so that's going to actually just go away. You're going to have that whole term drop off. And so when it's all said and done, I don't think I negated that. I don't know how to distribute in math. When it's all said and done, the double integral that I have to do is just minus y squared ds, okay? And I would just switch to polar. It's a really easy way to do that problem. If you switch to polar, you want to go the full 0 to 2 pi. You want to go 0 to 1. You can pull out the negative, I guess. Then you'll have an r squared sine squared phi, or theta in there, and then you got r dr d theta as the Jacobian. And so that's all really nice. You can basically just do that the way that you're used to, no real weird tricks in there. You'll get negative a quarter pi, okay? So that's kind of part 1, right? And now the idea is like I'm going to let like S2 equal S1, that disk, combined, formal term is unioned with S, okay? And that now is one of these regions like E, that is like a simple closed region. You can basically think of it as like a type 1. You can go from the disk up to the upper part of the sphere. So that whole thing is S2. And that is where I'm going to be able to do divergence theorem. So if I go ahead and set all that up, double integral over S2 f dot ds is really just by divergence theorem, triple integral over E of the divergence of f dv. And the divergence of f is just going to be actually quite nice in this problem. You would just get z squared plus y squared plus x squared. And then we have dv. So since E here is this upper half of the sphere, it makes sense to convert this problem now to spherical coordinates. So, we know in spherical coordinates this thing would just be equal to basically rho squared, right? And then if we switch to spherical, we will need the Jacobian for that as well. So if I put in my rho squared and my Jacobians, rho squared sine phi, right? And then I've got like d, let's say d rho, d phi, d theta. My rho goes 0 to 1, phi goes 0, that's the angle that comes down from z, and that would be pi over 2, up to pi over 2. And then you do need the full polar angle, 0 to 2 pi. And so if you do that thing out, not such a bad triple integral either. Basically, you'll just get 2/5 pi. And so now you can kind of put everything together, because you've got basically the surface integral over the entire thing, and you've got the surface integral on the disk down there. And so you should be able to take away the surface integral of the disk, and you'd be left with the surface integral of the top half of the sphere. And so let's do this in blue. Basically, the double integral of S2, right, of f dot ds. S2 is the one I just calculated, of S, right? S is just the top half of the sphere. That's going to equal the double integral of S2, which is my entire upper hemisphere, which I have, minus the surface integral of the disk, S1. And so you basically just do 2/5 pi minus negative 1/4 pi, and then you would get 13/20 of pi, and that's it. So that's kind of a neat problem, because it doesn't seem like you can do divergence theorem, but then if you set it up and kind of combine this closed disk with the upper half of the sphere, then you actually can, and then it's way quicker. Switching to polar, getting that amount of the surface integral over the entire thing, and then subtract out the disk, and you would be left with what they wanted, which was the surface integral across the top half of the sphere. All right. The last thing I want to do in this video is just prove some kind of quick identities. And a lot of this is kind of what you see in physics courses in college. So for this problem, let's just assume basically all conditions of the divergence theorem are met. And you basically just need to prove, assuming divergence theorem is at your disposal, that all of these identities hold, okay? So this first one, we want to show this surface integral equals 0, where a is a constant. So by the divergence theorem, right, this would equal the divergence of a dv, but the divergence of a, if a is a constant, right, you're just going to be taking partials of constants, and that would all equal 0, right? So you'll have 0 dv over e, and of course that's equal to 0. So that's all you got to do for that one. That's pretty quick. This next one, is basically saying that the volume of E, like the closed bounded surface, is actually equal to 1/3 the surface integral around the boundary of it. And given that F, the vector field, is X, Y, Z. Which is kind of an interesting formula, if you think about it. If you have this vector field, you can actually get the volume of it using this. And you can see that with divergence theorem as well. So if we just work with that part, the divergence theorem is going to say, oops, I want the 1/3 in there. So I have the 1/3 divergence of F dV, and then I got 1/3, and then divergence of F is just going to be partial of this with respect to X, which is 1, plus this with respect to Y, which is also 1, plus this with respect to Z, which is also 1. So you get basically a 3 in there, and then you can bring the 3 out, and it cancels the third, and then you just are doing a triple integral of like 1 dV, which we know is literally the volume of the surface E. Something we saw back in chapter 15. So that's kind of a neat way that you can find the volume of an object. If you wanted, you could do the surface integral of it, but you can also just do the divergence of it. But it does require a certain special vector field, that one. Okay, last one in here. I just want to show the curl of F dotted with ds. So basically the surface integral of the curl of F here is equal to 0. And this is true for arbitrary vector fields F. So again, using divergence theorem, I would have the divergence of the curl of F dV. And if I switch to my symbols, that'd be the del operator dotted with del cross F dV. And this, right, is something that we actually saw in another video. If you go back to our second curl and divergence video, I basically proved that was 0. And so there, at that point, I would just kind of utilize that previous problem, and we would get triple integral of E 0 dV, which, of course, again, is 0. And this kind of stuff is just so prevalent in a lot of physics, and I think that a fair amount of people in this class are going to go on to be physics majors. And so I kind of want you to see some of these things. Like when I remember taking exams in college with that, I basically remember just proving different vector identities and things like that, like we're doing here. And if you just have divergence theorem in the back of your head, a lot of these are super easy. But if you don't have divergence theorem, then they're kind of weird and complicated and things like that. So it's good to see.